The main thing I want to emphasize here is something I've emphasized already. When you do applied math, you are, by your very nature, doing approximate math. You are trying to apply theorems, which are rigorous things that can be proved using deductive logic, in, you might say, approximate ways, like making assumptions of independence, for example. When we apply this theorem, which is what I call the fingerprint theorem, we are assuming we can calculate moment generating functions for one thing. We are assuming that we got distributions whose moment generating functions are known. Distributions that we've talked about. In the discrete case, binomial, geometric, Poisson. In the continuous case, gamma, normal, exponential, chi-square. All those are very commonly used distributions. We make assumptions that our random variables are well modeled by those things, even though in reality they may not be perfect models. And so based on those assumptions, you can apply it, and you might then compute the moment generating functions and see that they happen to be equal on some interval around zero, some open interval around zero, like some interval centered at zero, for example. The conclusion is they have the same distribution. Again, not that x and y are equal. They might be modeling two different situations. Maybe your bowling scores and my bowling scores. But if somehow we find from our model that the moment generating functions seem to be equal, the conclusion is we have the same distribution for our bowling scores. Not equal, because on any given night when we both go bowling, we aren't going to get the same score necessarily, but they are modeled by the same distribution as the conclusion of this. The next important theorem was this one. Let x1 and x2 be independent random variables. It's an assumption of independence. In the theorem, we can certainly make that assumption because it's part of the theorem. When you apply the theorem, you need to ask yourself whether independence really seems reasonable or not. If it does, you go ahead and apply it, and you hope that it's then helps you come up with a reasonable model, in this case, for the sum of the random variables, like the sum of our bowling scores or something like that. x1 and x2 are independent. With these moment generating functions, let y be their sum. Then the moment generating function for y is given by the product of the moment generating functions for x1 and x2. And we did talk last time about how this does apply to more than just the sum of two random variables, but n random variables that are all assumed to be independent. The moment generating function of the sum is the product of the moment generating functions. And in your homework, I hope it came across that this is a very useful thing. We will talk about that maybe even right now. Let's go ahead and do that. You applied it to normal distributions. Another important situation where you applied it is to problem 44 about the distribution of the sum of independent chi-squared random variables. In this exercise, you will prove that the sum of a collection of independent, we have to assume independence here, chi-squared random variables also has a chi-squared distribution. You also have to specify the degrees of freedom. We assume x1 and through xn are independent chi-squared random variables with these degrees of freedom. Notice that since these degrees of freedom are not necessarily the same, that does mean this is not necessarily a random sample, because with random sampling, you assume you got independent random variables from the same distribution. They're all chi-square here, but they could have different degrees of freedom. So this is not the same as a random sample unless all these gammas are the same. We form the sum. The goal is to show that the sum y is a chi-squared random variable, or has a chi-squared distribution, with gamma degrees of freedom, where gamma is the sum of the gamma i's. Okay, so we apply the moment generating function theorem, the second one that I showed you, and ultimately the fingerprint theorem. You do these things in conjunction. The moment generating function for the sum doesn't have to be computed from the definition. Instead, it's the product of the moment generating functions for each of these things individually. This is very powerful. Okay, imagine what you would have to do to try to figure this out if you didn't have this theorem. What would you have to do to figure out the distribution of the sum? Analogous to what we did with in chapter 5 with adding exponentials and uniforms, we'd have to do an integral. In fact, we'd have to do an n-dimensional integral, not a single integral, not a double integral, not a triple integral, but an n-tuple integral over some, what? N-dimensional triangle? What? Well, it's actually not a triangle. It's called a simplex. In higher dimension, a simplex is kind of like a higher dimensional version of a triangle. Actually, it's a bit more general than that, but some sort of higher dimensional triangle is an example of something called a simplex. And you'd have to integrate over that, and you can't visualize it. Can you do the integral? Evidently you can, but this is a better method. Just multiply these moment generating functions and use the fingerprint theorem. But you do need to look them up. Of course, we've got our handy dandy table. Moment generating function for a chi-squared random variable with little gamma degrees of freedom is 1 minus 2t to the negative gamma over 2. Right? Because chi-squared random variables are gamma random variables with beta equal to 2 and alpha replaced by little gamma over 2. When you do that, when you replace beta with 2 and alpha with little gamma over 2, where little gamma has to be a whole number, 1, 2, 3, 4, 5, 6, etc., whereas alpha could be any positive number. Then you get a chi-square distribution with little gamma degrees of freedom. So coming back to the problem at hand, I hope you figured this out. You would get 1 minus 2t to the negative gamma 1 over 2 times 1 minus 2t to the negative gamma 2 over 2, etc., through 1 minus 2t to the negative gamma n over 2. And then, I hope it was clear, you need to add these exponents. They all have a common denominator of 2. Adding them all together means, negative gamma 1 minus gamma 2 minus gamma 3. We can factor out the negative sign and write that as negative gamma 1 plus gamma 2, etc., over 2 like that. And now is where you apply the fingerprint theorem. This is the MGF of a chi-square random variable with gamma 1 plus gamma 2, etc., through gamma n degrees of freedom. Which is exactly what the book said it would be. Your final step is applying the fingerprint theorem. The fingerprint theorem effectively, which could also be described as the uniqueness of MGFs, says that means the sum y equals x1 plus x2 through xn has such a distribution. That's described up there. It's got that MGF, so it's got to have that distribution. The MGF is like a fingerprint. It identifies the random variable, which is a really good thing. Okay, this is a good thing to know in applications. Try to hint at some along the way, including even today. Let's take a look at problem 45. It can be shown that the square of a standard normal random variable has a chi-squared distribution with gamma equal to 1. You can take that as an assumption. I would like to actually prove that, though. Before we do so, let's read the rest of the problem. That is, the random variable z squared follows a chi-squared distribution with 1 degree of freedom. Let x1 through xn be a random sample. So this is a random sample now from a normal distribution with mean, mu, and variance sigma squared. Use the previous exercise that we just talked about to show that this summation, on the next page it says, has a chi-square distribution with n degrees of freedom. Let's do the first thing. You didn't have to do what I'm about to do. You could just trust that when you square a standard normal random variable, you get a chi-square distribution with 1 degree of freedom. But let me show you that we can verify it, and you could even do this based on what you know, though realizing this is a good way to do it is not necessarily obvious. It's the CDF method again. CDF method for the distribution of z squared, where z is standard normal. Why use the CDF method? Why not use a moment generating function? I mean, we could try a moment generating function method maybe, but this is z squared. It's not z plus z. We're not adding random variables here. We're multiplying a random variable times itself. And there's nothing about independence here either. So we probably do need some other method, and the CDF method does work. What again is the CDF method? It would be finding the CDF first, using the definition of a CDF, and then differentiating it to find the PDF. Give this variable a name, or we could call it y. What's the CDF for y? I'll use little y as the variable name, since I'm using capital Y as the random variable name. As always, it's the probability that capital Y, the random variable, is less than or equal to the number little y. That's what it always is. That's what a CDF always is, whether it's discrete, continuous, doesn't matter. Again, the way you compute it depends on whether it's discrete or continuous. Do you add numbers or do you do an integral? In this case, we don't have to do either because we can use the relationship between y and z squared. We can relate y to z and use what we know about z, hopefully. First, replace y with z squared. We actually did do a problem like this before when we squared, what did we square, an exponential random variable, I think? Maybe it was a uniform, or maybe it was both, I'm forgetting. This one's a little trickier because with an exponential random variable or a uniform variable on the interval from 0 to 1, you never get negative outputs. Z, however, can be negative. So to say z squared is less than or equal to y really means the absolute value of z is less than or equal to the square root of y. And that absolute value can include negative quantities. So this is really the same as saying z itself is between negative square root of y and positive square root of y. By symmetry of the standard normal distribution about 0, and since square root of y and negative square root of y are the same distance to 0, I can say this is double the probability that z is between 0 and square root of y. That's symmetry there. Symmetry of this normal curve centered at 0. And this can be written as the probability that z is less than or equal to square root of y minus the probability that z is less than 0. And since z is continuous, we can write less than or equal to 0 as well. This is 2 times the difference of 2 CDF values for the standard normal distribution. It's like a capital F value and a capital F value there. In fact, this one's 0.5. I don't need to use the CDF, right? Because that's the median, 0 for a standard normal distribution. We did have that special notation, special to my heart. For the CDF of a standard normal, it's a capital phi. Oh, it's just so pretty. Capital phi of square root of y minus 0.5. 2 times capital phi of square root of y minus 2 times 0.5 is 1. This is the CDF for z squared. Y equals z squared in terms of this new letter y. So I got to differentiate it to find the PDF of y. The PDF of z squared, because y does equal z squared. Yeah, to differentiate this, I guess I need the chain rule. The inside function is square root of y. Its derivative would be 1/2 y to the negative 1/2. Should I put this on a calc gateway? No. This simplifies to capital Phi prime of square root of y divided by square root of y, which means I need to know capital Phi prime. I need to know the PDF for a standard normal, but I do know that. I've even got it memorized, I think. 1 over square root of 2 pi, remember that? There was also, for a general normal with standard deviation sigma, a sigma down here, not under the square root, but sigma's 1 here, because z is standard normal. Times e to the negative, it was x squared over, it was, what was it? X minus mu quantity squared over 2 sigma squared. Mu is 0 though, sigma's 1, sigma squared is 1. It simplifies to x squared over 2. But I'm replacing x with square root of y. So I get square root of y squared over 2. Oh, don't forget about my square root of y down here too. Oops, I was going to put it. I was going to put it down here. Sorry. Simplify this a little bit. 1 over. I'm purposely going to simplify this in a little funny way. Square root of pi times 2 to the 1/2 times y to the negative 1/2 times e to the negative y over 2. Why am I simplifying it that way? I've got the answer in my head. Going back to the table in chapter 4, remember we're using the CDF method here. This is supposed to be ultimately the PDF for our random variable. What's the answer supposed to be? It's supposed to be chi squared with 1 degree of freedom. That's what the book said the answer was. There's the PDF. We're using a different letter y instead of x, but it's the same kind of formula. We have an e to the negative x over 2 there, just like we had an e to the negative y over 2. Gamma is supposed to be 1. 1/2 minus 1 is negative 1/2. We have a y to the negative 1/2. Looking good so far. What about this thing? 2 to the 1/2. Oh, what about the gamma? What's capital gamma of 1/2? It couldn't possibly be the square root of pi, could it? Mathematica. What's capital gamma of 1/2? Oh, square root of pi. It had to be. But wait a minute, I thought gamma was like the factorial function. Isn't gamma of alpha equal to like alpha minus 1 factorial or something? Gamma of alpha is alpha minus 1 times gamma of alpha minus 1. Yeah, I think it's supposed to be like alpha minus 1 factorial. So does this mean, what if alpha is a half? Does this mean negative 1/2 factorial is square root of pi? What? Okay. The gamma function is more general than the factorial function. It just simplifies to factorials when alpha's an integer greater than or equal to 1. That's all. Yes, amazingly, gamma of 1/2 is square root of pi. That is the PDF for a a chi-square distribution with 1 degree of freedom, which is a gamma distribution. It's with beta equal to 2 and alpha equal to 1/2. That's what it was. Isn't that cool? I think this stuff is amazing. As long as you don't make a mistake, how it works out. Blows my mind. And it is useful. Coming back to this problem, number 45, we have now verified the first sentence. What about the rest of it? Second sentence, I guess, 2. Let x1 be through xn be a random sample from a normal distribution with mean, mu, and variance sigma squared. We want to show that this summation, again, the conclusion is it follows a chi-squared distribution with n degrees of freedom. The thing to realize here is that this fraction is the same as some other fraction squared. It's xi minus mu over sigma quantity squared. And you know, if xi is normal with mean, mu, and variance sigma squared, when you subtract its mean and divide by its standard deviation, you do get a z, you do get a standard normal. So we are adding up a bunch of independent standard normal random variables here. The independence comes from assuming this is a random sample. They're all like z squared, a bunch of z squareds. It doesn't matter that you get a subscript of I there. It doesn't matter. They're all a bunch of standard normal random variables being added up. They're squares being added up. So each one of them is a chi-squared distribution with 1 degree of freedom. And therefore, by 44, the summation is a chi-squared random variable with 1 plus 1 plus ... plus 1 degrees of freedom and 1's n degrees of freedom. Is this useful? Yeah, though not in a real precise way for us. We think about modifying this a little bit for a new result today. That'll help us come up with what are called confidence intervals for the variance and standard deviation. In applied stats, if you take that, later in the book, I think it's chapter 15, you get into something called the chi-square test, where this is related to the main results there. Chi-square goodness of fit test is one example of something you do in chapter 15. Very useful thing that lots of people use in statistics. Continuing looking at some important theorems here. It was this theorem, Theorem 7.3.4, that we called the Cornerstone Theorem. Let x1 through xn be a random sample of size n from a normal distribution with mean, mu, and variance sigma squared. Then x bar, the sample mean, which I remind you is a statistic. And I remind you what that means. That means it is computable from a random sample. It essentially has a formula based on a random sample. Random sample being a collection of n random variables that are independent and they're from the same distribution. In this case, normal with mean, mu, and variance sigma squared. That is also normally distributed with mean, mu, same mean. That's the unbiasedness. The expected value of x bar equals mu. But a different variance, sigma squared over n. We, again, actually knew that the mean of the mean is the mean before we talked about normal distributions at all in this context. And the variance of x bar was sigma squared over n before we talked about normal distributions at all. With this Cornerstone theorem, the new thing is that x bar is also normal. You'll also hear people say x bar, the sample mean, statistics, have what are called sampling distributions. That's what this is talking about when it says it's normally distributed. It means its sampling distribution is normally distributed. The distribution of a statistic is often called a sampling distribution. It's not mentioned in our textbook, but many other textbooks mention the phrase sampling distribution. Now, I'll remind you of what it means again in the future here. You might wonder, is this theorem really applicable? Because like when are your variables ever going to be exactly from a normal distribution? Perhaps never. Does that make sense? Well, remember, again, in applied math, you're always just doing approximations. The theorem in its pure form is true. It can be proved. But when you apply it, you're not applying it in its full purity, you might say, because maybe it doesn't technically apply precisely because maybe your population is not truly exactly normal. You just hope it's good enough. You hope it seems reasonably normal. And because of that, this theorem effectively means X bar should be reasonably normal. A normal curve should be a good approximation, give you good approximate probabilities, etc. And help you calculate good approximate confidence intervals, which is now our next topic. We want to be able to compute, this is kind of funny the way it's written, a 100 times 1 minus alpha % confidence interval to estimate a population mean mu. I haven't mentioned what a confidence interval is. So far, we've been doing point estimation. I forgot to show myself this whole thing. There I am. So far, we've been doing point estimation. X bar is called a point estimator for mu. An observed value of X bar is called a point estimate for mu. That's just one statistic and ultimately one number to estimate an unknown population parameter. How do you know how good it is? Maybe we want to give ourselves some cushion. That's where the idea of interval estimation comes in. And for the most part, we call interval estimates confidence intervals. There is one situation in regression where you call them prediction intervals, but mostly we call them confidence intervals. And we describe our level of confidence in them in this way as 100 times 1 minus alpha %. What a weird way to describe the level of confidence. I'll explain it here in a minute, but just realize typically this is a number close to 100%. The most common value that this takes on is 95%. If this is going to be 95%, I guess that would mean alpha is 0.05. Yeah, 1 minus 0.05 is 0.95 times 100 is 95. The most common value of alpha is 0.05. Now that's the most common value. It doesn't mean you have to use that unless the problem says to use that. But in real life, when you apply this, you don't have to use alpha equals 0.05, and you don't have to use 95% confidence. It's just kind of what people do most typically, because we're creatures of habit. Other common confidence levels include 99% confidence, maybe 90% confidence. Why wouldn't you want more confidence? Why wouldn't you want 99% or 99.9% or 99.999999%? Because there's a price to pay if you want more confidence. And sometimes that price is literal money. You might have to spend more money to get more confidence because you might need a bigger sample size. Yeah, usually that's what happens. The sample size N needs to be bigger to get more confidence, and well, that costs money. So there's always trade-offs, compromises between higher confidence versus not spending too much money, not going broke. We're trying to estimate a population mean mu. What is the answer here? Let me just jump to the chase here. Is that the phrase? Jump to the chase. Cut to the chase. Let me just cut to the chase here. The answer is capital X bar plus or minus Z sub alpha over 2 times sigma over square root of N is a 100 times 1 minus alpha % confidence interval to estimate mu. We're trying to estimate this population parameter mu using this point estimate X bar, this point estimator, I should say, and using some other numbers here, the sample size N, the population standard deviation. Wait a minute. If we don't know mu, why would we know sigma? Because we're just pretending we know sigma. to keep things simple at first. We're trying to keep things simple. And what's this? Z sub alpha over 2. We are assuming sigma is known. Z sub alpha over 2 is a notation that I have briefly talked about in class. More commonly, I've told you to read about it. That is a number on the horizontal axis. It's a Z, so evidently it refers to standard normal random variable, such that the area under a normal distribution with mean 0 and standard deviation 1, meaning also variance 1, to the right of Z sub alpha over 2 is indeed alpha over 2. This area equals alpha over 2. We have briefly talked about this notation before. It's been in the reading. It came up on the last exam in the context of a chi-squared problem. The subscript in this context always refers to the area to the right of the number under whatever curve you're talking about. In this case, the standard normal curve. Since there's a plus or minus there, couldn't I also maybe use the opposite of that number over here? Negative Z sub alpha over 2, which I guess by symmetry, this area should be alpha over 2 as well. By symmetry, that should be the same as Z sub 1 minus alpha over 2. It is. And it also means the area between these two numbers is 1 minus alpha. Hey, matching the 1 minus alpha right there. That's what the Z sub alpha over 2 is. In the most common case where alpha is 0.05, that means alpha over 2 is 0.025, and it means Z sub alpha over 2, Z sub 0.025, it turns out to be this the most common number used in statistics, 1.96, approximately. Close to 2. We are close to using the 68, 95, 99.7 rule. Not so surprising when you think about it, because if alpha is 0.05, 1 minus alpha is 0.95. 100 times that is 95, 68, 95, 99.7. When this area is 0.95, these two numbers are close to plus or minus 2. More precisely, plus or minus 1.96. To really confirm those with technology, I could do my calculator, go to my distribution menu, go to inv norm, area 0.975 to the left of 1.96, right? So the area to the right is 0.025. If I copy and paste this in, I should get 1.96. Yeah, very close. Probably the most common number used in statistics right there, 1.96. What if alpha is something else? Another common thing is 0.01. So alpha over 2 is 0.005, and the corresponding Z sub 0.005, can I do it from memory? I'll probably get it wrong. Seems like it's 2.3 something, I think. I'm forgetting. Well, that's pretty bad. I'm forgetting. I'd want 0.995 here. See if I was right. 2.5. Okay, I was wrong. 2.576 approximately is what's used there. It's probably a bad idea for me to guess. I just forget too much. I do remember the 1.96, and I'll probably remember that to my dying day. If alpha is 0.1, so that alpha over 2 is 0.05, then we're after Z sub 0.05. I'm thinking that's 1.645. I think I remember that one better. 0.95 there. I think this is 1.645. Yeah. About 1.645. These are just the most common ones to use, but you should be able to use other ones. Like if I picked alpha to be 0.03 for some strange reason, so that alpha over 2 is 0.015, and I need to compute z sub 0.015, the area to the left needs to be 0.985 if the area to the right is 0.015. Turns out to be about 2.17. I didn't know that ahead of time. Okay, so you should, in theory, be able to find this for any alpha. How do you use this formula? You're given data. This is how it's going to come up on the homework. Compute a 99% confidence interval to estimate mu. You'd be given some data, some numbers. Got to put them in your calculator. You got to compute the observed value of x bar. If you're using 99% confidence, you'd use this value of z, 2.576. You'd have to be given sigma. Don't compute sigma with your calculator. Your calculator will tell you sigma equals something, but don't use that. In this class, and probably in applied stats with Dr. Wetzel, don't ever, ever, ever use the sigma that your calculator gives you. Never, ever. It's wrong. Huh? Don't ever use it. If you need sigma in a problem on homework or tests, you'll be given it. Because the sigma from your calculator is computing a standard deviation estimate that's not based on an unbiased variance, it's based on a biased variance where you're dividing by n instead of n minus 1. We want our variance to divide by n minus 1, so s squared is unbiased, although we mentioned s, unfortunately, is not unbiased. But we use s anyway. You always use s, not sigma. Write that down. Always use s, not sigma. Don't ever, ever, ever use sigma from your calculator. Does anybody in the world use it? Probably people who want to buck tradition, who want to be rebels. But no, don't be a rebel in this class. You get points deducted. Okay, unless you don't mind having points deducted. Use s. You won't fail the course, but you'll get points deducted. Don't ever, ever use sigma on the calculator. So you're given sigma. You also know the sample size, use the formula. So just to make something up, maybe you get x bar is, observed value is 2.17. You're given sigma to be 1.3. Your sample size n is 25. To make it nice and simple, we're doing 99% confidence. So we say that means the z sub 0.005 is what we got before, 2.576. And this all implies that our confidence interval would be 2.17 plus or minus 2.576 times 1.3 over square root of 25. Or square root of 25 is 5. 1.3 divided by 5 is 0.26. By the way, this number, 0.26, sigma over square root of n has a name. It's called the standard error for the mean. I haven't mentioned that, but the book does mention it. Observed value. Well, okay, now it's not really an observed value. It's the standard standard error for the sample mean x bar when n equals 25. It's the standard deviation of the sampling distribution of x bar. There's that term again, sampling distribution. X bar by the Cornerstone Theorem, I'm sampling from a normal distribution at least, is normal with mean mu and variance sigma squared over n, standard deviation sigma over n, or sigma over square root of n, sigma over square root of n. And sigma over square root of n is called the standard error for x bar when n is the sample size. That's the z multiplied by z. We get a confidence interval of 2.17 plus or minus 0.670 if you want to. I usually, as a habit, use one more place of accuracy for my margin of error is what this is called compared to my point estimate. Not that that's technically the right thing to do. Usually you'd want these to be the same number of significant digits or at least the same number of places of accuracy. I kind of make a habit of going one more place. That's the plus or minus notation for the confidence interval. In interval notation, and I believe our textbook uses closed interval notation, it would be 2.17 minus 0.67, 1.500, say, to 2.17 plus 0.670, 2.840. Our textbooks uses closed interval notation. To tell you the truth, I probably prefer open interval notation. Does it matter? Not really. Kind of for the same reason it doesn't matter with continuous random variables whether you use less thans versus less than or equal to's. What is the interpretation of what we got here? We say we are 99% confident that this interval contains the true mean mu. That's what we say. But what does that mean? Hang with me. Let me restate what I just said. Based on what we've done, based on a random sample of size 25 from this population and getting this observed value of x bar, using 99% confidence as our target confidence level, we have computed this interval. It's an interval on the number line, centered at 2.17. The distance between the midpoint at 2.17 and the endpoints at 1.500 and 2.840, that distance is the margin of error, 0.670 in both directions. That's our interval. We are 99% confident that the true unknown mean mu is in this interval somewhere. 99% confident. Very confident. Does that mean the probability that mu is in this interval is 99%, 0.99? No, it does not. What? How could it not be? The reason is this, and this is almost a distinction without a difference, but bear with me here. The reason it's not, you can't say the probability that mu is in here is 0.99 is because probabilities are always before the fact calculations. I am about to compute a 99% confidence interval, but I haven't done it yet. In that context, if I'm going to use this procedure, I can say ahead of time the probability that my interval will contain mu is 0.99. But once I've done it, there's no more randomness. Mu is either in there or it's not. So you can't say the probability that mu is in there is 0.99. Really? I mean, if I were going to make bets, couldn't I take 0.99 as the betting odds of how likely it is to be in there, meaning very likely? If somebody really knew what mu was, yeah, I guess if somebody really knew what mu was, but nobody really knows what mu is, so that it's kind of a nonsense kind of question. Yeah, that kind of feels like a distinction without a difference. Is that the phrase? Distinction without a difference. Like, is it a big deal to think of it as a probability when it's really not? Yeah, it's probably not a big deal, but technically speaking, it's not a probability anymore. The formula is computed, however, by thinking about probabilities. Let me show you the calculation the book does in the case where it's 95% confidence. They say, okay, we know that if Z is a standard normal random variable, we know this probability is approximately true. That's what the calculator gave us. If Z happens to equal X bar minus mu over sigma over square root of n, and that would be standard normal if I'm sampling from a normal distribution by the Cornerstone Theorem, because I'm subtracting the mean, which I know is mu, and dividing by the standard deviation of X bar, which I know is sigma over square root of n. And if I'm sampling from a normal distribution by the Cornerstone Theorem, X bar is also going to be normal. This will be normal. Z will be standard normal. I can then replace Z with that, and then I can try to do some algebra to ultimately say, give this probability statement. And notice that these endpoints inside this thing right here are of the form X bar plus or minus 1.96 times sigma over square root of n, where 1.96 really is Z sub alpha over 2 when alpha is 0.05. So the formula is computed by doing probability calculations and some algebra. It's kind of tricky algebra. You should double check each step on your own. They're trying to go from this thing to isolate mu in the middle. That's the algebra. You should be able to reproduce this, including if I didn't use 1.96, but instead used a general Z sub alpha over 2 there and a negative Z sub alpha over 2 there, and put in a 1 minus alpha there. You should be able to reproduce the same kind of calculation I'm telling you right now, so you might want to practice it. 56 minutes in the class by the timer on the phone if you want to rewatch this. What did I say again? Should be able to reproduce this where you replace the 1.96 and the negative 1.96 with Z sub alpha over 2 and negative Z sub alpha over 2. And that number 0.95 becomes a 1 minus alpha. Should be able to redo these calculations to get ultimately the left and right endpoints for this interval. Well, there's the general definition of a confidence interval. The interval that I'm talking about, in particular, though, is in this theorem right here. Do notice, though, something I haven't really emphasized yet, that technically for this theorem to be true, it's got to be a random sample from a normal distribution. Kind of like the Cornerstone assumes normal distribution. But do people use this theorem even if they're not sampling from a normal distribution? They do. Remember, it's applied math, fuzzy math. We hope things are not perfect, but just good enough. But is there any justification for whether it's really good enough or not? There is. The central limit theorem. Let x1 through xn be a random sample of size n from a distribution with mean, mu, and variance sigma squared. The word normal is not in that first sentence. It's not the Cornerstone Theorem. It's not the theorem I just showed you with the confidence interval. I'm not assuming this population is normal. It's just got mean, mu, and variance sigma squared. Then for large n, x bar is approximately, there is the word normal, approximately normal with mean, mu, and variance sigma squared over n. And therefore, when I standardize, it's also approximately standard normal. Wait a minute, how would you prove this theorem? Large n, approximately normal. Large, approximately, those are vague words. Fuzzy math. As stated, this is not really a theorem. As Dr. Wetzel would say, it's a result. A result is a a deficient theorem. It's good enough for our purposes. How large is large? Oh, I don't know. Probably n is in the thousands is probably large enough. Maybe n is in the hundreds is even large enough. Maybe n equals 50 is even large enough. It kind of depends on how big sigma is, and sigma squared is kind of, and how far away from normal the population is. Those are all the factors that affect how big n needs to be large. And how approximate is approximately normal? It depends on those factors as well. So again, as stated, this is not precise enough to be a true theorem, but it's good enough for our purposes. If we want to prove it, we need a precise statement. Is such a precise statement possible? Yes, but it's too complicated for us. This is good enough. And what this theorem does then is, you might say, pseudo-justifies applying this formula even when the population is not normal. And people do apply this formula, even though when the population is not normal. But they are aware of the fact that this theorem is only technically true when the population is normal. And so they do check. I've got some data. Maybe I make a stem and leaf plot or a histogram, and I say, does it look normal or reasonably close to normal? If it does, let's go ahead and use this. If it looks very skewed, we probably should avoid this unless n is very large. They do have those kind of heuristics that they apply on the job. And it would be good if you did so too in the future. What are we ultimately after here with these confidence intervals? The main thing we're after, chapter 7 and 8 here, is estimating means. That's the main thing of concern, estimating mu. I just showed you the confidence interval estimate for mu when sigma, the population standard deviation, was known. But that's an unrealistic assumption. If you don't know mu, why would you know sigma? At the beginning of chapter 8, it's all about adjusting for that reality. But it gets more complicated because we have to adjust for that reality. We have to estimate sigma with, like, well, I guess S. Sigma, population standard deviation, S, sample standard deviation. But if we do that, there's a price to pay, as there always is in statistics. There's always a price to pay. We have to do something more complicated in this case. And we also end up losing a degree of freedom and can't use Z anymore, our old friend. We need a new kind of random variable called T. T distribution. Students T distribution. Discovered by somebody with the last name of Gossett. Hey, there's Gossett professors at Bethel. And the Gossett professor, well, one retired. Nathan Gossett's dad retired. The Gossett professors at Bethel have 2 T's at the end of their name, but the Gossett who discovered the student's T distribution only has 1 T. I guess the second T was used for the T distribution. That small joke was just brought across to me today for the very first time by Nathan Gossett. That's what he's like. That's the joke about us Gossetts and the Gossett of the student T distribution. Anyway, before we can get there, we have to do something else. We have to talk about estimating sigma squared and sigma, population variance and population standard deviation. This is the first theorem that's relevant for that. Let x1 through xn be a random sample from a normal distribution with means mu and variance sigma squared. Once again, for this to be a true theorem, to be provable, that population distribution has to be exactly normal. But when people apply it, they apply it even when it just seems reasonably normal. Then this weird random variable, n minus 1 s squared over sigma squared, which can also be written as the sum, has a chi-squared distribution with n minus 1 degrees of freedom. Why not n degrees of freedom? Since we're adding n things here. It's because we lost a degree of freedom when we replaced mu with x bar. This is related to problem 45. In chapter 7, problem 45 in chapter 7 has this summation. Summation I goes from 1 to n of xi minus mu squared over sigma squared. This is summation I goes from 1 to n of xi minus x bar squared over sigma squared. The mu got replaced with an x bar. Because of that replacement, we lost a degree of freedom. Why? I'm not going to explain it because it's too complicated. We got to use n minus 1 degrees of freedom instead of n degrees of freedom when mu got replaced with x bar. Y is equal that. That's just a calculation with the formula for s squared. We could quickly confirm that. All right, it is n minus 1 over sigma squared s squared like that. Use the formula for s squared from chapter 6 as the summation I goes from 1 to n of xi minus x bar squared divided by n minus 1. That's the formula for s squared. Back in chapter 6, hey, the n minus 1s cancel, leaving you with the summation I goes from 1 to n xi minus x bar squared over sigma squared. So this equality of these two things is the easiest thing to verify. The harder thing to verify is that it really has got a chi-squared distribution with n minus 1 degrees of freedom. It's kind of related to 45, but it's not the exact same thing as what we just did with problem 45 in chapter 7. But the fact that we did problem 45 from chapter 7 and got a chi-squared distribution with n degrees of freedom, you might say makes this a little bit more believable, even if it's not a proof. Okay, great. How is this useful? This is useful by this derivation, which I won't go through the details of, to come up with a formula for the left and right endpoints of another kind of confidence interval. This is still interval estimation, not point estimation. What are we trying to estimate here? We're trying to estimate the population variance sigma squared. Theorem says if you got a random sample of size n from a normal distribution, once again, it's a normal distribution. To be truly accurate, it's got to be normal, but to be approximately accurate, we just hope n is big by the central limit theorem. Then the lower and upper bounds L1 and L2 for a 100 times 1 minus alpha % confidence interval for sigma squared are given by these two formulas here. N minus 1 times s squared divided by a certain critical chi-squared value. Notice that in both of these formulas, that's a lowercase chi-squared. And it's got a subscript, just like with z, that's either alpha over 2 or 1 minus alpha over 2. Those subscripts, remember, just like on the last exam, represent areas to the right. This picture is the key to interpreting those. This is supposed to be the graph of the PDF of a chi-squared distribution with n minus 1 degrees of freedom. You'd use the table in the back of the book, just like in the last exam, or your calculator, to figure out these critical values. The subscript here being alpha over 2 means the area to the right of it is alpha over 2. The subscript here being 1 minus alpha over 2 means the area to the right is 1 minus alpha over 2, meaning the area to the left is alpha over 2. This is not symmetric about the origin or anything else. It's a skewed graph. It's a right skewed distribution. These numbers are not plus or minus each other like they were with z. When we compute this confidence interval, we are not getting an interval centered on s squared. It's not S squared plus or minus something. It's the left endpoint and the right endpoint. This kind of confidence interval is not centered on S squared. That's okay. 1 minus alpha is still the probability of being between these. And we are 100 times 1 minus alpha % confident that our true population variance sigma squared is somewhere between these numbers. So how would you use this? You'd have some data. Certain random sample from a population that's normal, or at least approximately normal. You got a certain value of n, plug it in. You compute S squared. From your calculator, that would mean you'd have to compute S and then square it. Then you got to find these chi-squared values from the table in the back of the book. I forget if the calculator does it or not. I don't think it does it? Well, okay, you could kind of use the chi-squared CDF if you wanted to. With some experimentation, it would not be pleasant. Like if you were after chi-squared sub 0.025, you'd have to guess, based on, I don't know, 5 degrees of freedom. Maybe it's 10, probably not. Not good enough yet. If alpha over 2 is 0.025, I'd want this to be close to 0.975. So use something bigger than 10. 15. That went too far. The answer is somewhere between 10 and 15. I could continue trying to narrow it down, but that would be unpleasant. It's probably better to just use the table in the back of the book. In a spreadsheet, there's probably an inverse chi-squared, if I remember correctly, but I forgot without actually bringing it up. The next section is about the student's t-distribution. And there's this definition of what a t-distribution is. For the moment, you don't need to really understand this definition. All you need to do is I will have you go ahead and use this theorem on at least one homework problem. It's not that hard. Theorem says, let x1 through xn be a random sample from a normal distribution. Oh, there's that normal distribution again. Again, to be technically correct, it's got to be a normal distribution, but people use it when it's approximately normal. Like when n is large and it's not too skewed. If you're after a 100 times 1 minus alpha % confidence interval on mu to estimate mu, x bar is your point estimate again, plus or minus a margin of error again. The only difference between this margin of error and the other one, 2 differences, I guess, is we use S instead of sigma and T instead of Z. You got to use the t-distribution table in the back of the book or your calculator. You got to use n minus 1 degrees of freedom. Because we're using S instead of sigma, we need to use n minus 1 degrees of freedom. You can use this formula without understanding everything else in this section. Look at the examples. Study the examples. Use the table in the back of the book. Plug the numbers in. Okay? Work toward fuller understanding, but we'll have to do that in class on Thursday.